What if the most dangerous volcano on Earth is one you would never recognize as a volcano at all? No cone, no towering mountain, no lava river crawling down a blackened slope, just forests, lakes, steaming ground, quiet valleys, maybe even entire cities, all resting on top of something so vast and so misunderstood that for decades we've been imagining it in almost the wrong way. Because when most people hear the word supervolcano, they picture one thing: the end. A planet-darkening eruption, ash covering continents, crops failing, civilization collapsing, a geological apocalypse waiting underground. But the truth is stranger than that. The real danger of a supervolcano is not that it's simply a bigger volcano, it's that it doesn't behave like a normal volcano at all. And the more scientists study these systems, the more unsettling the picture becomes. Because what we used to think was a giant underground bomb may actually be something much more complicated, and in some ways, much harder to understand. Supervolcanoes don't just erupt, they build, they breathe, they deform, they leak heat, release gas, crack the crust, and quietly reshape the land for thousands of years before anything dramatic ever happens on the surface. They can look calm while enormous geological forces move beneath them. And that may be the most disturbing part of all. By the time a true catastrophe begins, the process behind it may have already been unfolding for far longer than anyone realizes. That is why some of the most beautiful places on Earth are also some of the most deceptive. A peaceful lake can be the flooded scar of a collapse so violent it changed the atmosphere. A national park can be the roof of a heat engine buried deep inside the crust. A city can be built across land that has risen and sunk for centuries because something beneath it never truly went quiet. And once you understand what a supervolcano really is, it becomes impossible to look at those places the same way again. Because the first thing we got wrong about supervolcanoes is the shape. A normal volcano is easy for the human brain to understand. It rises above the landscape. It looks dangerous. It announces itself. A mountain of fire feels like exactly what it is. But a supervolcano is often too large to appear dramatic in the way we expect. Instead of building a steep cone, it can create something broader, flatter, and far more deceptive. A caldera, a giant collapse basin formed when enough magma leaves the subsurface that the ground above loses support and drops inward. That means some of the most powerful volcanic systems on Earth don't look like mountains at all. They look like land. And that is where the misunderstanding begins. Because if a volcano doesn't look like a volcano, people stop thinking about it like one. It becomes scenery. It becomes a lake, a valley, a geothermal attraction, a place people hike through, photograph, or build on. The violence that created it disappears into the background. But the Earth doesn't forget what happened there. It stores that history in buried ash, fractured rock, collapsed crust, chemical residues, mineral changes, and hidden heat. And sometimes, it keeps storing energy there long after the last major eruption. That is what makes supervolcanoes so fascinating and so unnerving. They are not simply ancient disasters. They are active geological systems. And to understand why that matters, you have to go beneath the surface. For a long time, the public image of a supervolcano was almost cartoonishly simple. A giant underground chamber filled with liquid magma, sitting there like a pressurized tank waiting to explode. It's an image that feels intuitive. It also happens to be one of the biggest reasons people misunderstand these systems. Because scientists now know the underground reality is far messier than that. Beneath a supervolcanic region, you usually don't find one perfect cavern of glowing lava waiting for a movie-style detonation. What you find instead is often a sprawling, layered, evolving system of hot rock, partially molten material, crystal-rich mush, gas, fluids, fractures, and magma intrusions moving through the crust over time. That distinction sounds technical, but it changes everything. Because if a supervolcano is not a single molten bomb, then it does not erupt in the simple way people imagine. It has to become eruptible, and that may be the most important revelation in the entire story. A supereruption is not just pressure building until something pops. It may require a long and unstable process in which enough melt accumulates, enough gas becomes trapped, enough fresh magma enters the system, and enough of the overlying crust weakens for the whole structure to cross a threshold. That means the real danger may not be a chamber waiting. It may be a system assembling itself, quietly, gradually, underground. And this is where supervolcanoes stop being dramatic and start becoming eerie. Because if their most important stage happens before the eruption, during the build-up, the reorganization, the hidden preparation, then the most dangerous part of the process may also be the part that is hardest to observe directly. And that is exactly the problem volcanologists face. We can detect earthquakes. We can measure gases escaping from the ground. We can track uplift and subsidence with satellites. We can use seismic waves to image broad structures beneath the crust. We can study crystals and ancient deposits to reconstruct what happened in the past. But we still cannot watch a supervolcanic system clearly enough in real time to know with certainty when deep unrest is simply geological activity and when it is becoming something much more dangerous. That uncertainty is not because scientists are clueless. It's because the Earth is operating on scales that are both enormous and subtle at the same time. Imagine trying to understand the inner state of a machine the size of a region, buried kilometers underground, moving in slow motion over centuries and only revealing itself through scattered tremors, changes in gas chemistry, thermal anomalies, and slight vertical shifts in the land. That is what we are trying to interpret, and sometimes the signals are deeply ambiguous. A swarm of earthquakes can mean magma is moving, or hot fluids, or crustal adjustment, or fracture propagation. Ground uplift can suggest pressure buildup, but it can also reflect fluid redistribution or localized inflation that never leads to eruption. Gas emissions can change because magma is rising, or because hydrothermal pathways are opening in a system that remains non-eruptive. In other words, a supervolcano can look alarming without being close to catastrophe. But it can also be changing in meaningful ways without looking as dramatic as people expect. And that is where the real fear begins. Because human beings are terrible at living with hidden risk. We want clean warning signs. We want certainty. We want the Earth to behave like a machine with obvious alarms, red lights, sirens, countdowns. But geology doesn't work that way. The biggest systems on this planet often whisper before they roar, and sometimes they whisper for a very long time. That is why supervolcanoes are so psychologically disturbing. They force us to confront the possibility that some of the most powerful processes on Earth do not announce themselves in ways that feel obvious to human intuition. And the deeper you go into the science, the less comfortable that becomes. Because once you stop imagining a supervolcano as a giant explosive chamber and start seeing it as a living underground system, a new question takes over the entire story. If these places are not simply waiting to explode, then what exactly are they doing right now? That question matters more than people realize, because a supervolcanic system does not spend most of its life erupting. It spends most of its life changing. Fresh magma can intrude from deeper levels of the crust or mantle. Older material can partially melt again. Crystals can grow and then be reheated. Volatiles like water and carbon dioxide can become trapped or escape. Hydrothermal fluids can weaken rock. Faults can be reactivated. Pressure can build in one zone while being released in another. The whole system can remain geologically alive for astonishing spans of time without ever producing the cinematic eruption people are fixated on. And that changes the meaning of active. Most people hear that word and imagine immediate danger. But in volcanology, active can mean something much stranger. A system that is not dead, not stable, not fully quiet, but also not necessarily on the verge of a major eruption. It means a landscape that is still processing energy. And some of the most famous supervolcanic regions on Earth are doing exactly that. Yellowstone is probably the most mythologized example in the world.
For many people, it has become a kind of geological horror story, a place often described online as a sleeping apocalypse, a hidden doomsday machine buried beneath a national park. But Yellowstone is more interesting than that, and more scientifically revealing. Because Yellowstone is not terrifying simply because it could, in theory, produce a very large eruption again someday. It is terrifying because it shows how alive a giant volcanic system can remain, even when it is not erupting.
The park's famous geysers, hot springs, fumaroles, and mud pots are not just tourist attractions. They are surface expressions of an enormous heat flow system below. The ground in parts of Yellowstone has risen and fallen repeatedly over time. Seismic swarms occur there. Hydrothermal features can shift, intensify, migrate, or explode. The crust beneath the region is not quiet. It is moving. Not chaotically all the time, but enough to remind scientists that Yellowstone is not some ancient dead scar. It is an active magmatic and hydrothermal system that continues to evolve. And one of the most important discoveries about Yellowstone is also one of the least cinematic. Much of the material beneath it is probably not stored as a giant lake of fully molten magma. Instead, a large portion exists in partially molten zones, crystal-rich, viscous, thermally active, but not necessarily ready to erupt in the way the public often imagines. That may sound reassuring, but it actually makes the science more complicated. Because if the system is not simply full of liquid magma, then the critical question becomes, what would it take to mobilize enough of that material, reorganize enough of the melt, and weaken enough of the crust to produce something much larger? And that is not an easy question to answer. The same basic problem appears again and again in other supervolcanic systems around the world. In New Zealand, Lake Taupo looks almost impossibly peaceful. But beneath that calm surface lies one of the most active silicic volcanic systems on Earth. Taupo has produced eruptions of extraordinary violence in the geological past, and even its smaller eruptive episodes would be catastrophic by any normal human standard. That is another thing we often get wrong. We imagine the threat of a supervolcano as all or nothing. Either nothing happens, or the world ends. But real volcanic systems are not that binary. A caldera system can generate moderate or large eruptions that are not technically supereruptions and still cause immense devastation. It can produce ashfall, pyroclastic flows, regional atmospheric disruption, ground collapse, or long-term instability, without reaching the absolute upper limit of what it is capable of. In other words, a supervolcano does not need to do its worst to become a disaster. That matters because it means the true hazard is broader than the public narrative allows. We tend to focus on the most extreme scenario because it is dramatic, but in many cases the more plausible risks are also the ones most likely to be misunderstood or ignored. And then there is Toba. If Yellowstone became the modern symbol of supervolcanic fear, Toba became the ancient one. Around 74,000 years ago, the Toba system in what is now Indonesia produced one of the most extreme eruptions known from the recent geological past. The eruption was so vast that it created the giant caldera now occupied by Lake Toba, a landscape so beautiful today that it almost hides the scale of the violence that formed it. For years, Toba was treated as the ultimate example of a supervolcano nearly changing the course of humanity itself. One influential idea suggested the eruption may have triggered a severe volcanic winter and caused a dramatic population bottleneck in early humans, reducing our species to a tiny remnant. It was a powerful theory, and like many powerful theories, it spread fast because it felt like exactly the kind of story the Earth would tell if it wanted to remind us how fragile we are. A volcano so large it almost erased us. But the more scientists studied the evidence, the more complicated the picture became. Toba was absolutely colossal. There is no question about that. Its ash deposits, collapsed structure, and eruptive scale are undeniable. But whether it nearly wiped out humanity in the way people often claim is far less certain. Human populations may have been affected unevenly. Some ecosystems appear to have persisted more resiliently than once assumed. Climatic effects may have varied in intensity and duration depending on where and how they are measured. Once again, the reality was not less interesting than the myth. It was more nuanced, more difficult, and more revealing. That pattern shows up everywhere in supervolcano science. The biggest mistake is rarely that people invented the danger out of nowhere. It's that they simplified it into something easier to imagine. And perhaps nowhere does that simplification become more unsettling than in southern Italy. because Campi Flegrei may be one of the most disturbing examples of all. Unlike Yellowstone or Toba, this is not a vast wilderness or a remote prehistoric scar. Campi Flegrei exists in one of the most densely populated and historically layered volcanic regions on Earth. It is woven into the fabric of modern human life near Naples, where people live, drive, work, and raise families on land that is geologically restless in ways most cities never have to think about. And Campi Flegrei has a habit that makes it especially unnerving. It rises and it sinks. This phenomenon is known as bradycism, the slow uplift and subsidence of the ground as fluids, gases, and magmatic processes shift beneath the surface. Over time, the land can physically move enough to alter coastlines, damage buildings, crack infrastructure, and trigger anxiety in entire communities. Think about how strange that really is. Not an eruption, not lava, not fire in the sky. Just the earth beneath a city slowly lifting and dropping, because something underneath is never fully still. That is the kind of geological behavior that changes how you think about danger. Because it means a supervolcanic system can affect human life long before any catastrophic eruption ever occurs. It can distort the ground, release gases, alter the hydrothermal system, generate swarms of earthquakes, and create a persistent state of uncertainty. And uncertainty is hard to live with. At what point is a restless system simply being restless? At what point is it building towards something larger? That line is one of the hardest things in earth science to define. And it may also be the most important. Because one of the most surprising discoveries about giant volcanic systems is that many of them may spend far more time in a state of partial instability than we once realized. Not eruption-ready in the dramatic sense, but not comfortably dormant either. That is a very uncomfortable category. It means the Earth can host regions where immense energy remains stored and active without crossing the threshold into disaster, at least not yet. And that brings us to one of the most haunting ideas in the entire field. What if the most important transition in a supervolcano's life is not the eruption itself, but the moment it becomes capable of one? That is a much deeper scientific problem than it sounds. Because a supereruption doesn't happen simply because magma exists underground. Magma exists beneath many volcanic systems that never produce anything remotely close to a supereruption. The real question is, what transforms a large, long-lived, partially molten system into something mechanically unstable enough to fail catastrophically? That transformation may involve repeated injections of hotter magma from below. It may involve remobilization of crystal-rich mush zones. It may involve volatile buildup, crustal weakening, fracture connectivity, roof failure, thermal maturation, and internal reorganization across multiple depths. And if that sounds complex, that's because it is. A supervolcano is not one event waiting to happen. It is a giant geological process trying to become possible. And that is a far more unsettling idea than a simple countdown. Because a countdown implies clarity. A process implies ambiguity. A process means the Earth can spend centuries, maybe even millennia, assembling the conditions for something enormous while revealing only fragments of what is really happening. That is why many volcanologists are less interested in the fantasy question, when will it blow? And more interested in the real one. How does a supervolcanic system organize itself into eruptibility? That question may determine everything. And it becomes even more unsettling when you realize that some of the same signs we fear might actually be part of what prevents the worst-case scenario. This is one of the strangest truths in volcanology. Activity is not always bad news. Sometimes, a volcanic system releases energy through smaller intrusions, degassing, localized deformation, hydrothermal venting, or minor eruptive episodes that reduce pressure instead of escalating it. A restless system can, in some cases, be a system that is venting stress rather than storing it. That sounds almost backwards. We tend to imagine movement as evidence that disaster is approaching. But in geology, a completely sealed and silent system is not automatically safer than one that is breathing. In some cases, a system that cracks, leaks, and adjusts may actually be avoiding a larger catastrophic failure, which means that instability can sometimes be part of stability. And that idea should completely change how you think about supervolcanoes. because it reveals just how misleading our instincts are. We are drawn to obvious violence, eruptions, ash clouds, lava fountains, explosions. Those things are easy to fear because they are visible. But some of the most consequential changes in a giant volcanic system happen long before anything visibly dramatic occurs. Heat moves, crystals remelt, fluids circulate, gas accumulates, rock weakens, pressure redistributes. Pathways form, and the landscape above may remain deceptively ordinary the entire time. That is why supervolcanoes are not just dangerous geological structures. They are pattern recognition traps. They produce exactly the kind of incomplete, ambiguous, slow-building signals that human beings are worst at interpreting emotionally. Too quiet to panic over, too active to ignore, too vast to picture clearly, too rare to feel real, until you realize the scars they left behind are already all over the planet. And the scale of those scars is almost beyond comprehension. When geologists talk about a true supereruption, they are not talking about a bigger version of an ordinary volcanic disaster. They are talking about a different class of planetary event altogether. Mount St. Helens in 1980 was devastating and unforgettable, but it belongs to a very different scale. Krakatoa was world famous, but still far below the upper end of volcanic violence. Even Tambora in 1815, which caused the year without a summer and affected global climate, was still not the largest kind of eruption Earth is capable of producing. A true supereruption belongs to the uppermost extreme of explosive volcanism. It can eject more than 1,000 cubic kilometers of material. That number is so large it stops feeling meaningful unless you force yourself to imagine what it means physically. Entire regions buried, atmospheric circulation disrupted, skies altered, ecosystems overwhelmed, the crust itself collapsing inward as the support below is removed. This is not a mountain exploding. It is part of the Earth's surface giving way to what it has just unleashed. And yet, for all that scale, one of the most remarkable things scientists have learned is that these systems may spend enormous spans of time not as fully molten monsters, but as unstable mixtures of partially melted rock, crystals, and volatile-rich zones that are capable of changing state. That means the Earth's most extreme volcanic potential can exist not as a permanent catastrophe in waiting, but as a condition that may emerge only when enough hidden pieces line up. And that should make you uneasy. Because if the most dangerous stage is the stage of becoming possible, then the real story of supervolcanoes is not simply about destruction. It is about hidden transformation. It is about landscapes that look finished, but are not finished. It is about regions that appear stable but are only stable on the surface. It is about the disturbing fact that the planet beneath us is never as still as it seems. That may be the deepest reason supervolcanoes fascinate us. Not because they are guaranteed to erupt tomorrow. Not because they are all secretly overdue. That idea, by the way, is another major misconception. Volcanoes do not run on clocks. They do not miss appointments. Geological systems are governed by evolving physical conditions, not human expectations of schedule. A place that erupted long ago is not automatically building toward an imminent repeat just because enough time has passed in our minds. What fascinates us is something more primal than that. Supervolcanoes reveal that Earth contains forms of power so large and so patient that they can disappear into the background of normal life. A lake can be a wound. A valley can be a collapsed scar. A steaming hillside can be a pressure release valve. A city can be built across a breathing caldera. And a place that feels quiet can still be participating in a process far older and far more violent than anything human civilization has ever experienced directly. That is what makes the subject so haunting. Not only the destruction these systems are capable of, but the way they hide inside ordinary landscapes. Because once you understand that, something shifts. You stop seeing Yellowstone as just a park. You stop seeing Taupo as just scenery. You stop seeing Toba as just a lake. You stop seeing Campi Flegrei as just urban ground. You start seeing them for what they really are, windows into a version of Earth that is deeper, hotter, stranger, and less predictable than the one human beings prefer to imagine. And maybe that is the real reason we were wrong about supervolcanoes. We thought the fear belonged to the eruption, but the eruption is only the final expression. The real story is everything that happens before it. The hidden heat, the unstable crust, the trapped gases, the slow inflation and collapse, the long silence that is not really silence. The fact that some of the calmest places on Earth are calm only because we are looking at them on the wrong timescale. That is the part that changes how you see the planet. Because when you stretch your sense of time far enough, the ground beneath us stops feeling permanent. It starts feeling active, temporary, in motion. Not chaotic every second, but alive in ways that are easy to miss until you know what to look for. And that may be the most unsettling scientific truth of all. The Earth does not need to look extreme to be extreme. Sometimes the most violent systems on this planet are so large that they vanish into the landscape. Sometimes the biggest dangers are hidden not by distance, but by familiarity. And sometimes the strangest mysteries in nature are not the ones buried in outer space or the deepest ocean. They are the ones quietly sitting beneath places people call beautiful. If you want more real science about the most terrifying, mysterious, and extreme places on Earth, subscribe to the channel. Because the deeper we look into this planet, the less normal it becomes.